everyone. Today we are going to start section 3.3 and I will answer a couple of homework questions that I received by email. I also wanted to announce that even though we're not meeting in class tomorrow, Alan has offered to go into the classroom to help her work homework problems. So if you are struggling with homework or you just need a little extra time to sit somewhere and do homework problems, Alan, our TA, will be there during the regular class time tomorrow. So she will arrive when we normally start class, and she'll be there through the whole class and to answer your questions. Please use her as a resource, and I will see you again on Thursday. But today we are going to start section 3.3, which is differentiation rules. We're not going to go all the way through, so we'll finish up 3.3 and work on 3.4 on Thursday. So these are basic differentiation rules, which means that for you, that every time you take a derivative, you're not going to have to go through finding the limit as h approaches 0 of f of x plus h minus f of x all over h. I'm sure you agree that that gets cumbersome after a while, so we have some basic differentiation rules that you need to get down, and once you have them down, they will very much simplify the process. The first one is the derivative of a constant. So if you have a constant function like f of x is equal to c, then the derivative of the function, this is the derivative, with respect to x is equal to 0. So if you're taking the derivative of a constant function, you always get 0. Now this notation, df dx, means the derivative of the function with respect to x. Now if you just have d over dx and the function itself is in a parenthesis, those are instructions. That says take the derivative of whatever's in the parenthesis with respect to the variable on the bottom. So this is with respect to x. So part of what we're working on today is notation, so you know what you're being asked for. So for example, if I have the function f of x equal to 3, then I could say the derivative of that function is equal to 0, because that function is a constant. I could also say d dx of 3. This tells me take the derivative of 3. That's equal to 0. And remember, we have a couple other notations as well. So you could say f prime of 3, or f prime of x is equal to 0. And you could also say y prime. So these are our notations. Here, y prime is equal to 0. All right, so that's our first rule, the constant rule. If you have a constant, the derivative of a constant is always 0. Second rule for today is called the power rule, and this is the general power rule. So if you have any real number power, then if you take the derivative of x to that power, so this is like x cubed or something like that, then what happens is the power comes down to the front and we reduce the power by 1. So this is the old power. It's now a multiple, and we subtract 1 from that power in the power position. So the power has to be defined, so you can't have something undefined up there. But we bring the power down and reduce by 1. Sometimes this means that your power ends up fractional or negative, so just be aware of that. So if I have something like y is equal to, let's say, x to the 8th, and I want to take the derivative, dy dx, the power itself comes down to the front, so this 8 comes down to the front, and the x stays where it is, so we have x, and then we reduce the power by 1, so 8 minus 1 gives me the 7th power. Now, a lot of times we don't just have plain old x for our function. We have some sort of constant in front of that x, and which brings me to the constant multiple rule. So if you have a constant in front of whatever thing you're taking the derivative of, the constant multiple stays. It's like hitching along for the ride. So constant stays where it is, and we multiply the constant by whatever we bring down to the front. So let's say I have x to the 8th again instead, but instead we have a multiple in the front. So y is equal to, this time, 3x to the 8th. Now the power rule still applies. So this is 3 multiplied by the function x to the 8th. So what I'm doing is I'm bringing this 8 down into the front, but what happens is there's already something there. So whatever is already there, when I multiply, I end up with 8 times whatever is already there. I still reduce my power by 1, and my new function, 24x to the 7th. Now, if I wanted to find the derivative of some functions here, differentiate is another word for find the derivative. So differentiate means find the derivative. And looking at these functions here, the first one, y is equal to pi squared divided by 6 plus 3 times the 4th root of 7. All right, looking at those, well, pi is a number, as is 6. 3 and the 4th root of 7, all numbers. So when we find y prime here, these are all constants. And the derivative of a constant is just 0. Really, there are 2 of them there. So 0 plus 0 gives me 0. Now, one thing I want to note is you notice that I changed from y to y prime. When you are going through and writing your derivatives, it's not appropriate to just say that this is equal to 0 plus 0, because it's not. The derivative of that function is equal to 0 plus 0, but the function itself isn't. So make sure that you notate the derivative somewhere along the line. So same thing here. If I want to differentiate or take the derivative, I notate it as f prime of x. So f prime of x, using the power rule, the 4 comes down to the front, and I have x, and I subtract 1, gives me 4x cubed. Some more practice here. So g prime of t. Here it's negative 8 times t to the first. So here if I bring this first power down, I get 1 times negative 8 times t to the 0 power. Anything to the 0 power is equal to 1. So 1 times negative 8 times 1 gives me just negative 8. If we go to number 4, if I want to use the power rule on something in the denominator, the first thing I have to do is bring it up into the numerator. So I'm going to write it in its equivalent form. This is equal to 9 times s. Remember that if you're bringing something to another side of the fraction, then we change our sign on the exponent. So 9s to the negative 7. So if I am looking for h prime, I'm going to bring that negative 7 down to the front, multiply it by the 9 that's there. And when I subtract 1, be careful which direction you go when you're negative. So negative 7 minus 1 gives me negative 8. So negative 63, s to the negative 8. And typically what we do is we give things back in the same form they were given to us. So that means bringing the s down to the bottom of the fraction, and h prime of s would equal negative 63 over s to the 8th. All right, number 5, writing our fraction. fractional exponent, so this y is really equal to 8 times x. Remember, the index goes on the bottom, so to the 3/5. So when I take the derivative, I have 3/5, bringing it down, times 8, and then we have x. I'm going to subtract 1, so 3/5 minus 1 in our power. Y prime is equal to 24/5 x. 3/5 minus 5/5 gives me -2/5. And then we give it to us in the way it was given, or give it back in the way it was given to us. So since it's negative, I'm going to bring it to the bottom of the fraction. I already have the 5 there. This was a 24. So this is the 5th root of x squared on the bottom. All right, for this next one, we need to write that as a single power of x. So I have x to the 1/2 on the top, and x to the -1 if I bring the other one. So this is -4 x to the -1/2. All right, taking the derivative, f prime of x is -1/2 times -4 x. -1/2 minus 1 gives me -3/2. -1/2 times -4 is 2, and x to the -3/2 power, which, giving it back in the same form, means that I have 2 on the top. On the bottom, I have the square root of x cubed. Square root, not cubed root. And there's my derivative. Now these have all been one-term derivatives, but it does not, it's not limited to one term. So you could have something with multiple terms, and the sum rule allows us to take the derivatives of something that are more than one term. So this basically says if I want to take the derivative of 2 things that are added together, then I get the derivative of one plus the derivative of the other. We use this for multi-term functions. The other function that I want to go over the derivative of is the derivative of e to the x. So if you take the derivative of e to the x, you get e to the x. So it is its own derivative, and we'll talk a little more about that later. But e to the x, the derivative of e to the x is e to the x. All right, so if I want to differentiate this function, we've got a bunch of different pieces of this function now, and what we're going to do is find each derivative individually and then put it all together. So if I am looking for g prime of x here, I'm just looking at this term by term. First term, I'm going to bring the 5 out to the front, multiply by the 7 that's there, reduce my power by 1. All right, second term, 5 on the bottom is really like 1/5, so I'm bringing my 2 out to the front, so I have 2. I had 1/5 already there. Reducing my power by 1 gives me x to the first. All right, looking at this one, I have a first power to start with, so bringing that out to the front, and I'm going to reorder and put the square root of 5 out here. And we reduce our power by 1, gives us x to the 0 power. And this last part, I have a constant, so the derivative of a constant is just 0. So simplifying, g prime of x is equal to 5 times 7 gives me 35 x to the 4th plus 2/5, or 2x over 5, 2/5 x, minus, This all simplifies into just plain old square root of 5, because x to the 0 power is 1, and plus 0, we can just leave it off. All right. Last problem of new stuff, and then we are going to start on Thursday with what's called the product rule, but I don't want to get into any major rules while we are distant. So we're going to start on Thursday with the power rule. For now, this is the last new problem, and then I have a couple of homework problems to work. So here, a of t is equal to 5 over t minus 12 times the cubed root of t to the 4th minus 5e to the t. So I'm going to reformat it just to get us so that it's easy to work the derivative first. So this is 5t to the negative 1 power. And minus 12, if I write that as a fraction, I have the 4/3 power. Minus 5e to the t. Now remember that the derivative of e to the x is just e to the x. So if I'm going to look at that last term, I'm just going to end up with the same thing all over again. So a prime of t is equal to negative 1 times positive 5 t to the negative 2 minus 4/3, so that comes down, times 12 t. 4/3 minus 3/3 gives me 1/3 to the 1/3 power, and minus 5 e to the t, because the derivative of e to the t is e to the t. All right, cleaning that up, a prime of t is equal to negative 1 times 5 gives me negative 5 on the top, and I'm going to make this t squared on the bottom. All right, as far as the other one, 3 cancels into 12, we're left with 4, so minus 16, and I have the cubed root of t, and minus 5 e to the t. So this has been some practice of really the power rule and the addition rule, and when we come back on Thursday, we'll start with this product rule. Now, a couple of homework problems that I've received by email are these ones here, and section 2.5, number 21 is the one I wanted to start with. And this is the kind that we were supposed to identify where the function is not continuous. So if we're going to identify where this function is not continuous, then if I rewrite this as 1 over sine of 2x, we need to figure out where the sine of 2x is equal to 0. So sine of 2x is equal to 0 if you remember right, for the sine function, that's the one that does something like this. So if we are talking about x equaling 0, then sine of 0 is 0. The other place where it crosses the axis here is at pi. But if I plug in x equal to pi, then what I get is 2 pi here. So I need to make sure that whatever it is multiplied by 2 gives me pi. So pi would be equal to 2x, meaning that pi over 2 is equal to x. So those are our two places where this function is not going to be continuous, at pi over 2 and x is equal to 0. Now, in order to write that, we need to make sure that we hit them all, because what happens is sine will continue on like this forever, and we need to make sure that we hit them. So the way that we do that is we use some sort of x equal to k pi over 2, where k is an integer. If you look in the back of the book, I'm not sure if they used this exact notation, but this is my preferred notation. I use K's. Sometimes they use N's. The letter that you use is really arbitrary, so my favorite is K, so that's what I use. Now, number 25, similar instructions. We're looking to see where that function is not continuous. If you think about the bottom of the function first, we need to see if that is going to be equal to 0 at any point. It's not, because you have a squared thing plus a squared thing, so this thing is always going to be greater than 0. So the bottom is okay. Now, so we're talking about the top. X on the top doesn't matter. It's okay. Tangent, though, is sometimes undefined. So tangent, if you're thinking about the unit circle, that's a terribly lopsided circle. But if you're thinking about the unit circle, the tangent function is undefined at pi over 2 and at 3 pi over 2. So that's when our slope is vertical, even though it doesn't appear it right here. But that's when our slope is vertical, so that's when tangent is undefined. So if we try and figure out how to write that, now remember, you could go around this time and hit it, you could go here and hit it, you could keep going here and hit it, and you still go into those undefined places. So here, x is equal to, we'll call it k pi over 2 again, where k is an odd integer. We can put any restrictions we want on there. So you can also, if you want to have k be any integer like we did last time, then you could call that 2k minus 1 pi over 2. So now it means that if k is any integer, the 2k minus 1 part forces it to be odd. So, so there's an idea there. All right, last couple. So number 33 on 2.5 says to find the limit of the secant of y secant squared y minus tangent squared y minus 1. So we need to figure out some way to simplify this. So I'm going to plug the y equal 1 in. So the secant of 1 times secant squared of 1 minus tan squared of 1 minus 1. Now, the 1 on the front is just going to go away because 1 times secant squared just gives me secant squared. What I'm really looking at for trying to simplify this thing right now is this part, secant squared minus tangent squared. Smells like a Pythagorean theorem to me. So I'm thinking about the ones that have secant, and I know that secant squared theta, oh, bad spot, secant squared theta is equal to 1 plus tangent squared theta. So if I bring that over to the other side, that means secant squared theta minus tangent squared theta is equal to 1. So putting that into our function, that means I have the secant of 1 minus 1 gives me secant of 0. I'm just going to cross that out. Gives me the secant of 0, and the secant of 0 is equal to 1. Secant of 0, reciprocal of cosine of 0, and we have 1. All right, last one. If we are looking for, this is 3.1 number 29, there are some applied problems in there. If we're looking for how fast an object that's being dropped is going after 2 seconds, what we're looking for, if we have our position, then the first derivative of a positioned function is equal to speed. So I want to find h prime of t, and we're in section 3.1, so that's the limit as h approaches 0 of f of t plus h. So that is 100 minus 4.9 times t plus h squared minus 100 minus 4.9 t squared all over h. Simplifying, 100 minus this t plus h squared, remember, is t squared plus 2th plus h squared. So I have 4.9 t squared, and then minus 4.9 times 2 is 9.8 th, and then minus again 4.9 h squared minus 100 plus 4.9 t squared all over h. Simplifying, my hundreds cancel, t squareds cancel, my h's, there we go like this, to get rid of those, and I have negative 9.8 t, I forgot my limit. I was sitting here simplifying the difference quotient. All right, so negative to 9.8 t minus 4.9 h, and if we let h go to 0, that's negative 9.8 t. All right, so at t equals 2 seconds, then we would plug in 2 for t, and we get the speed, negative 9.8 times 2, and we get 19.6 meters per second for our speed. All right, there were a couple other questions from section 3.1, but I will be going over some of those in class. And again, I encourage you to go and during class time and go see Alan if you are working on homework. You can work together on homework. It'd be a great opportunity to catch up if you're running a little bit behind. Otherwise, I will see you on Thursday, and feel free to email me any questions that you have. Thank you.